Welcome to Rock Talks by DrTed. I'm a retired medical doctor who finds myself now falling in love with geology. What I love about geology is the history of the Earth, revealed through rocks, through fossils, erosion, tectonics, eruptions, and metamorphosis. I'm not a trained geologist, and in fact I welcome the input of listeners like yourself who know better than me and can lead me to better understand the science that surrounds us all. In this video, we are going to look at a triple bed of Rugose corals that I am squatting on here in this photo. This bed extends for almost 2.5 kilometers in a remarkable exposure. But more on that later. We're going to travel to the Spring Mountain National Recreation Area northwest of Las Vegas. The Spring Mountains are capped by Mount Charleston. At 11,916 feet elevation, Mount Charleston is the highest peak in Clark County and the 8th highest peak in the state of Nevada. Unlike the Sierra Nevada mountains further to the west in California, the Spring Mountains and Mount Charleston are not largely granite, but composed mainly of limestone, meaning this entire mountainous structure used to be the floor of an ancient ocean, namely the Great Basin. Looking at a geologic map to get a little more oriented, we have Las Vegas to the east, with the nearby Red Rock Canyon with its Keithstone Thrust Formation very nearby. Over the mountains to the west, we have the town of Pahrump, Nevada. And then in between these stands the Spring Mountains, capped by Mount Charleston. Let's take a closer look here at the geology map. The large area indicated by the light purple color and the abbreviation PMB is known as the Bird Spring Formation. This is the dominant formation that caps the Spring Mountains in general and Mount Charleston in particular. The Bird Spring Formation consists largely of limestone, dolostone, filled with prominent chert nodules and layers. But our focus in this video are the fossils that are common throughout the formation, specifically corals, crinoids, brachiopods, gastropods, all marine life. In fact, almost anywhere you look in the Bird Spring Formation, you're likely to see the odd rugose or horn coral, or the tabulate coral Syringophora, also known as tube coral, or various brachiopods and other shelly mollusks. But we're going to be talking about a very specific bed of mainly rugose horn corals. Let me give you a little bit of a preview here. So for just a quick introduction to this structure that I call the Triple Horn Formation, what we find here is 3 layers of rugose or horn corals. A bed up on top here, then this in the middle, then this lower bed. Each of these beds are separated by a layer of blank limestone, somewhat probably of an extinction event between here, and then again at the top. As we'll see as we study this further, this structure gives us a remarkable ability to study how these corals grew on the ancient seafloor. And what's more remarkable than just this one location is that this same triple layered formation extends laterally in both directions for over 2.5 kilometers. It goes up and over this ridge and then down the other side and then up the next ridge. There's actually about 5 separate ridges here where this same triple rugose coral layer is found. I think this gives us also a remarkable opportunity to use biology, the life here in this limestone, as somewhat of a ruler to help us calibrate the geology that's going on here. It may give us some
inference as to how long it took for this, say, 4 feet of limestone to be laid down and preserved.
So what are these Rugose corals? These are artist conception models of solitary Rugose corals as they might have appeared in ancient ocean beds. This Rugose coral is the dominant fossil at play in our structure here, and the reason for the name Triple Horn Ridge. Rugose corals grew in shallow seas, much like modern corals. While there are over 1,000 species of Rugose corals identified by paleontologists, many share the basic idea of a horn-shaped structure, oriented with the wider end at the top, where the actual animal resided. The animal referred to as a coral polyp, and its tentacles and central mouth reached towards the light above. While tentacled animals are partly carnivorous, many have a form of algae embedded symbiotically in their tissues. The photosynthetic capabilities of the algae contributed to the nutrition of the animal and did therefore require sunlight. Sunlight therefore demands that the animal reach towards the light vertically, and any change in the environment that blocks the sun will contribute to the death of the coral. Here's what the Rugose corals look like embedded in our limestone formation. About 1 inch round at the top and about 4 to 6 inches in length or height, tapering to the smaller horn point at the bottom. Paleontologists believe these segments represent a sort of annual growth type characteristic. Now, in this view, I'm skin diving with my son Rudy, who lives in Hawaii. Many coral beds today grow at rates anywhere from a couple millimeters per year to more. Antelope coral, for example, has been shown to grow occasionally as much as 8 inches in a single year. But modern antelope corals are very different than our Rugose horn corals. Antelope corals do not show the segmented annual growth rings that Rugose corals display. Here is an artist's conception of the anatomy of the polyp that resided at the top level of the Rugose coral. Really, this is a jellyfish upside down instead of freely floating through the ocean. It's attached to the top of a structure of its own making. As it grows, it makes a bigger cup on top of the previous ones, slowly growing in length and in caliber. And these rings are felt to represent probably annular growth rings. Rugose corals don't have a particularly well-designed foot or root, so it's easy for them to be tipped over in the mud. But when they fall, they grow the next cup, turning back up towards the sun, so they will often be curved overall. Here's an example of one fossilized Rugose horn coral that has eroded away out of the limestone matrix, slightly curved, smaller pointed down and to the right, with the advancing larger end to the left and up. The successive rings here are felt to be an annular pattern, making this probably about 6 years old. But again, our focus today is not on the few scattered fossils, but on one remarkable exposure of these Rugose corals, where 3 to 4 successive beds of in situ or in position coral grew successively, one on top of the other, and extended for not only yards, but miles. But before we look in greater detail at our particular Rugose coral bed, let's review some basic paleosedimentary history. In the past, this area of the Earth was a huge, shallow sea. This is why we refer to it as the Great Basin. The Mojave is a large subportion of the Great Basin. In this shallow sea, there was life, certainly small floating life, known as diatoms or coccoliths or foraminifera. And as these animals died, their small bodies, rich in calcium and silica, drifted down to the bottom of the ocean floor, making a mud. But our story starts at a certain time with a certain layer where the light, the temperature, and the chemistry favored the growth of a bed of crinoids. Now, crinoids are stalked-based animals that look somewhat more like plants. But similar to corals, they actually have living animals building and inhabiting these stalks. This is what crinoids look like in our limestone bed. The crinoid layers, interestingly, are more yellow or tan limestone, and they're preserved specimens, unlike the Rugose corals, are mostly broken and tumbled stalks. Now, after this crop of crinoids lived and grew and died, another layer of calcium-rich mud was laid down, but something changed. I don't know if it was the depth of the water or the light or the temperature or the chemistry that changed, but the resulting climate seemed to favor now a complete change in fauna. The conditions now favor the growth of our horn or solitary rugose corals. Note that this crop grew upright, heading up to the sun, but then it was overwhelmed by some event. I'm not sure what. Perhaps it was a toxic layer of ash from a volcano, or a layer of mud that suddenly smothered our horn corals. But in any case, another layer of mud was laid down. But eventually, again, conditions returned to normal, and again it favored a second crop of rugose horn corals. This cycle of extinction and mud repeats, followed sometime later again by a third layer of rugose horn corals. This here is our triple horn coral layer. But now something changes. Again, either the temperature or the depth of water, something stops the growth of our rugose corals, and a few more layers of mud are laid down, but for some reason, a couple layers above, the conditions now favor the growth of syringopora, a form of colonial tube coral. Here is what syringopora looks like in our beds. These tiny tubes are technically also little rugose corals, but they are small and grouped tightly together in colonies and referred to as tabulate corals. I again often use their common name, tube corals. Now, in the middle of this tube coral bed, you might find an occasional horn coral, but 99% in this layer is this one syringopora species, a sort of monoclonal dominance that spans kilometers in area. It's not just a patch for a few yards. This entire layer is nothing but tube corals. Whereas down below, these same layers extend for miles with nothing but rugose corals. Now, moving on in time, moving up in layers, we find that limestone was laid down, and this time there's very little in the way of fossil activity. But instead, a different phenomenon is found. The chemistry here favored the precipitation of what's called chert, which is mostly silica formations that precipitate out of the mud. Now, there are various theories of what phenomenon actually leads to the formation of linear or nodular chert beds, theories that we might examine in some future discussion. But just note that in some areas, these chert beds are massive and again, very widespread. Let me show you here one example, not far from our horn coral ridge, where the layers of dark chert repeat every 6 to 12 inches for perhaps 20 feet to 30 feet in overall thickness. But finally, getting back to our mud, again, the chemistry changed, light or temperature or something, and interestingly, we now see another deposition of a lighter tan layer again. And guess what? This layer is again rich in crinoids. So these aren't just age-related changes. There must be something in the climate that favored these various species to grow at different time. Now, we're going to stop our progression here. Obviously, the layering did not stop here. The evidence is that scores of further layers were laid down on top of our layers here, probably thousands of feet of further layers. This led eventually to enough pressure and temperature that produced the lithification, or the turning into stone of this mud, turning it into limestone and the corals themselves into actual fossils. Eventually, climatic conditions changed, and possibly from uplifting of this layer, the lake went away. But now something else very interesting happened. The tectonics of the earth began to be a major factor. And so our bed was now turned into stone, but was lifted up at an angle of about 25 to 30 degrees. Almost everything in our area in the Bird Spring Formation is at this angle. So our limestone now, tipped up at an angle, was now under the effect of rain and wind and snow and sleet. So basically erosion took place slowly over time, leading to what we now have today. An inclined set of limestone cliffs that we scramble over. When we come to our triple rugose corn layer, wherever the erosion has exposed a horizontal surface, we see only the ends of the coral. Something that looks sort of like this. Here is an actual photo of this exposure. Zooming in, we can see these 1 to 2 inch coral heads that were once reaching up towards the sun above. Here's some other examples of these horizontal exposures, including the one in the upper right, which was the very first time that I discovered this bed of rugose horn corals, not knowing at that time that this was going to extend for kilometers in both directions. Now, getting back to our limestone bed, if we find a vertical exposure instead of horizontal, the corals look different because we are seeing them in their longitudinal axis now on the side. This is what it would look like, and as we zoom in on that, we see each little coral standing 4 to 6 inches tall as they grew in place in this location over 3 successive generations. Remember that these layers of limestone that we explore today at one time extended for miles across the Great Basin, covering an area the size of Nevada, Utah, Arizona, and Colorado combined. And our Rugose corals probably extended much further than they do today through this particular layer of limestone. But once again, the area was uplifted and exposed again to wind and rain, and large amounts of overburden were eroded away, leaving the rising staircase of ledges that we see today. If we look closer, we can see our 3 layers of Rugose coral here, and they continue on unabated, 3 layers going on for yards, for miles, in many directions. And these 3 layers consistently throughout only Rugose corals. If we look at the area from above, here is the ridge where I first found the triple horn layer. But further exploration revealed that the formation was exposed on the next ridge, and then later I discover it on the previous ridge, and down again to the 4th ridge. Then I found a big area of erosion where this layer had been lost, but as I continued to go north, I found it again exposed, again the triple horn layers. Overall, we have 2.5 kilometers as the crow flies, but also if you measure each of these 5 separate exposures and add up the exposure, the curved or angular exposures themselves, we actually have about 2.5 kilometers of actual exposure of this triple horn formation. Here are some other examples of these three layers in different places, some of them close up. As we explore further, we find again the same triple layer of coral, but in this location, the limestone matrix is softer than usual. And so in some areas, it is eroded away, leaving the corals, which are a much harder silica-rich minerals, standing like a small forest of mini tree trunks. So, I'd like to now consider some conclusions that we might draw from this formation. But before I do, allow me to share with you that I'm going to be drawing certain conclusions that might impact our perception of the history of the Earth. Many scientists believe that our Earth is about 4.5 billion years old. But there are others who believe that we have a young Earth age, perhaps only as old as 6,000 years. Also, many scientists believe that the source of the limestone was gradually accumulated calcium and silica, again in the bottom of ancient oceans. This is something that probably took place over millennia, and again in ancient seas. Others believe that these limestone layers occurred rapidly in flood-type mud flow deposits. And they reference the concept of the biblical flood. Now, that particular story suggests that the flood lasted 40 days and 40 nights. So we're just going to keep these ideas in mind as we draw our final conclusions here.
Let's take a little closer look now at one segment of our triple Rugose horn coral formation and see what conclusions we might draw from this. Let me first state that this layer is about just under 4 feet, about 3.75 feet in thickness, all totaled. As you look at it, you see again, obviously, that these corals grew in the vertical position almost everywhere. Now, like in any forest, there will be a few limbs or branches or trees that might fall over as the growth is going on from waves or other actions in the water. But in general, it's clearly vertically oriented throughout, suggesting that this was an in-position growth. This wasn't a bunch of fossil corals that were tumbled in here or thrown in a jumble by a flood or by a landslide. These corals each grew here. Now, I've called this 3 layers, but really, as we've said, while this one looks pretty well like a single layer, this bottom one often looks like actually 2 layers with a little extinction event in between. And this top one actually looks like 2 or 3 layers, at least 2 probably, that grew continuously. Some of the lower ones clearly have tumbled down, but in an orderly fashion, allowing the upper layer to continue to grow. So actually, I would say that we probably have 2 full cycles of growth here, probably 1 here, and probably 2 down here. And as we said before, these corals are clearly have annular growth lines on them, segments. And so just on average, I think it's reasonable to say that each one of these corals is probably at least 5 or more years old, which would suggest, again, that we have possibly 5 years of growth, 10, 15, 25 probably years of actual horn coral growth. This layer here can't be growing when this one is growing. They can't be simultaneous because this one would have been under the mud at that time, and corals don't grow under mud. So overall, I think we have a minimum of 25 years just based on the corals. Well, what about these layers of limestone in between, this extinction layer? Something happened here that stopped the coral from growing. There's almost no life, or at least no horn coral growth in this layer, suggesting that whether this was something chemical that changed, or whether this could have been a sudden flood of mud, that's possible. So we don't know for sure if this was a rapid deposition, as in a mud flow or a landslide, or whether it was a gradual deposition that could have taken millimeters per year or perhaps centimeters per year. If it was an immediate fast disposition all these 3 times, then again we have about 25 years of time in front of us here. If, however, these layers were more slowly deposited, and I've had a geologist here that suggests by looking at the nature of the limestone here, he doesn't think it was a rapid mudslide. He thinks it was gradual sedimentary processes. Let's just say that this was maybe another 5 years, and this is another 5 years. So if that's the case, if this was more typical gradual deposition, then I think we easily have 5, 10, 15 for the extinction layer, 20, 25, 30, easily 35 years of time represented in this layer. And again, since this is just slightly less than 4 feet, about 3.5 feet, that would suggest about 10 years per foot of growth. Now, I don't know for sure what happened below this, and there are thousands of feet of limestone below, and at one time there were hundreds or thousands of feet of limestone above. And so I don't know whether all of that down there was deposited slowly or rapidly. It could have been either, or could have been both. But I feel fairly confident in saying that this 4 feet of limestone represents at least 3 or 4 decades of time. Certainly, this layer could not have been deposited in 40 days and 40 nights, or in 120 days, or even a year. This layer must have grown at a time when there wasn't a lot of climactic, turbulent, geologic, or fluvial activity going on. So what I really like about this is that the biology here gives us sort of a ruler, because we know approximately how long it took for each of these layers to grow. It gives us a ruler to calibrate the geology. If we didn't have the fossils and all you had was 4 feet of limestone, it might be harder to determine how long did it take to deposit this. Could it have happened in one 4-foot mud flow, or was this something that had happened gradually? Because of the biology here, I feel comfortable in saying that this particular chunk must have been at least 3 or 4 decades of time. Thanks.
Now, if any of these observations that we've made are true, and since the Bird Spring Formation can be over 5,000 feet thick, I'm wondering if we can use our biologic ruler here, which suggests approximately 10 years per foot of limestone, to extrapolate that the Bird Spring Formation represents perhaps something over 50,000 years of deposition time. I hope you found this video useful and informative. As I said at the start, I'm a geology enthusiast. I'm not a degree geologist, so I welcome your comments and your corrections to my observations. You can leave your comments here in YouTube. Please do be civil. Or you may write me directly at geoted@icloud.com. If you'd like to be notified about future DrTed geology videos, please click the subscribe button below.